All right. Well, welcome, y'all. Thursday, nearing the end of the week. It's not Friday, but so close. So, last class we talked about. Let me make certain this is all good. Yep, good. We talked about wires make magnetic fields, and we did right-hand rules. And we found the I gave you the equations for the magnetic field due to an infinite wire. At the very end, I gave you the equation for magnetic field due to an arc of wire. And those are fairly straightforward. We did a problem that combined what we learned last week and then what we learned on Tuesday. So we said, hey, I got two wires. What's the force per unit length they experience due to each other? And the whole punchline, one makes a field, the other experiences a force due to that field. So we found the direction of the field due to one of the wires, where the other one was, and then we used that to find the force. So it used the equation for the magnetic field due to a current carrying wire. It used the equation for the force per unit length for a wire in a magnetic field. And it was lots of fun. So good. And we also learned that there's two right-hand rules. So let's just, right off the bat, there's right-hand rule 2.5, but I'll remind you of that in a second. Let's just make up a random question. A wire carries current to the left and a magnetic field pointed up. What is the direction of the force on that wire? Is it A, into the page, B, out of the page, C, let's see what other options would be reasonable here, up or down? So, because really the challenge at this point in time is the right-hand rules. The math is whatever. But the right-hand rules are where it's going to get, those are kind of the funkiest. So that's what we've kind of practiced the most in class. So a wire carries current to the left and a magnetic field pointed up. What is the direction of the force of that wire? A reminder to you all, it is helpful to draw a picture. That's how I will start explaining it. You can certainly try it without the picture, nothing wrong with that, but that is always the recommended strat. Just do a quick little sketch. There's my face for online people, so when I show this. And yeah, which right-hand rule do I use? Uno or dos? One or two? Alright. We'll go to a minute 10. Alright. Oh yeah, look at the answers. 5, 4, 5, 10, 15. I'll wait a bit more. I'll wait till 1:30.
I was really panicked.
No, you're fine, you're fine. There's someone else also alone. And you weren't alone. Alright. 5, 4, 3, 2, 1. Alright, so like I mentioned, we're going to draw a picture. So the current goes to the left in a magnetic field that's pointed up. So which right-hand rule do you use? Actually, kind of during my office hours, thought of a way that may help you remember. That left is terrible. It's kind of down to the left. So whenever you see the word force, one way you can help remember this is the strongest finger on your hand is the thumb. And so your thumb points in the direction of force. I don't know, maybe that's helpful, but I don't know, I feel like that's kind of nice. So if you ever want to find the force, you know your thumb is going to point in the direction of force because your thumb's real strong. So you point your fingers in the direction of current, you make your palm point in the direction of the magnetic field, and your thumb points in the direction of the force. Now, reminder to you all, so online, fingers point in the direction of current, palm points up, thumb points in. It's very awkward, but to kind of do. But the answer is into the page. Let's just into the page, so that's that. And I think we were basically 50-50 on the answer there. Yeah, look at that. Remember that current is positive charge flowing. Current is defined as positive charge flowing, so we didn't have to do any flip-floppy thing. But if this was a negative charge going to the left, then the answer would be out of the page. Negative charges are the opposite rule as positive charges / current. Okay? So great. This was right-hand rule number 1. Direction of force. Thumb is really strong. That's force. Let's do the other one. I have a current carrying wire. I have a current going out of the page. What is the direction of the magnetic field to the right of the wire? Is it up, down, left? Let's do out of the page or into the page. Sure. I have a current going out of the page. What is the direction of the magnetic field to the right of the wire? Again, drawing a picture is always handy. And this is the wording that you can expect on the test. This kind of wording. Out of the page is out of the page, into the page is into the page, up is to the top of your paper, down is to the bottom of your paper, left is to the left of your paper, right is to the right of your paper. I'm not going to do any north, south, east, west nonsense because that just gets confusing. Ooh, yeah, we're getting another 50-50 answers. Always interesting. So we'll go to 115. Close it out in 5, 4, 3, 2, 1. All right, so same strat. Draw a picture. We have a current carrying wire going out of the page, so we draw it like this. A dot is out of the page. We care about a spot to the right of it. Who cares how far? It could be close, could be far. It doesn't change the answer. Call it point P, P for point. So this one, our thumb points in the direction of current. So we point our thumb in the direction of current. We point our fingers in the direction of the point that we care about. And then you can just say the palm is in the direction of the magnetic field, or you can swing your fingers 90 degrees, pick your poison. When I do this, it makes a nice shadow, so it's easier to see. But thumb in the direction of current, P is to the right. So this is going to be up. The magnetic field is going to point up. The way to remember this, to kind of check your answers here, is to remember what the magnetic field looks like around a wire. It looks like a circle. The magnetic field around this wire looks like a circle. So when we're finding the magnetic field at a certain spot, it's just the tangent line to that circle. That's kind of one way conceptually to understand what we're doing. So like here on the bottom, it's to the right. Here on the top, it's to the left. Here in the top left, it's down to the left. It's the tangent line to that circle. Now, whether that circle is counterclockwise or clockwise, you have to do the whole right-hand rule to kind of figure that out. But that's the logic here. That's what we're doing with this right-hand rule, is just finding the tangent line to this circle. But there you go. How do you get better at these? You just do a whole bunch of them. You write down the rules in your note card so you don't mix up which one's which. This is, I don't know, not too much more I can kind of say to help remember it. It's just one of those things. So the answer is up. There you go. Tons of these practice ones in the problem set. So many. For this exact reason, because it just takes practice. Okay, I introduced right-hand rule 2.5, kind of at the end of class, last class. And this said, so at the end of class, we started to talk about arcs of wires that kind of make a circular path. And so I said, if you have a wire going in a circle, or even a square loop, literally just some kind of closed loop, right-hand rule 2.5 is a little bit of a shortcut to find the magnetic field inside of it. So if you have a loop of wire, you can kind of swing your fingers around it, kind of make your fingers go in the direction of current, and your thumb points the direction of magnetic field inside it. So like this one, it's going from above, it's looking kind of counterclockwise. Oh, my thumb points up, the magnetic field points up. For this loop here, I curl it the other way, my thumb points down. I mean, I guess I'm still curling. No, it's in here. The magnetic field points down. So, the magnetic field in a loop of wire, you can still use the normal right-hand rule number 2. Just literally pick any spot on that wire. So let's, for example, pick this right side of the wire. The current on this right side is going into the page. We could define it. So that's why it's going into the page. You can still use the right-hand rule 2. Thumb points into the page, the point is there, swing it 90 degrees, I still get out of the page. And then as my finger kind of goes around it, you see it doesn't matter where you pick. So, do whatever is best for you. This is a shortcut. Shortcuts are not something you need to know. So, up to you, but it is handy. Alright, this is how I actually taught you all in the first place, so nothing new here. Okay. So speaking of a loop of wire, here's the equation for it. So I gave you for an arc of wire. So that's right here. The arc of wire was mu naught I times theta over 4 pi r. If I have a full circle, theta is 2 pi. So if I have a full circle, theta is 2 pi. And if you just plug in 2 pi right there, in fact, I'll just write it out. B equals mu naught I 2 pi over 4 pi r. Well, the pi's are going to cancel. 2 and 4 kind of cancel. The 2 goes away and this 4 turns into a 2. And we get our equation. We get the equation for a loop of wire. Mu naught I over 2r. Mu naught is 4 pi times 10 to the minus 7. Just a number. You just plug in 4 pi times 10 to the minus 7 in your calculator. I is the current, 2 is 2, r is the radius of this loop. And this is the magnetic field at the dead center of this loop. Only the dead center. So the logical question is, what is the magnetic field if I'm not at the dead center? What's the magnetic field if I'm here? Don't worry about it. That's my answer to you. You don't need to worry about it. I don't even know what the equation is gross for it and not worthwhile. Now, then you may be like, why? This is so specific. Why do I care about the magnetic field at the dead center of a loop of wire? We'll see. There's a reason. For now, just trust me that this is useful. Remember, everything builds, y'all. We started with a straight wire, and then we made it into a curved wire, a loop of wire. We're going to do that to build the last one that actually is physically useful in the real world. Everything builds to something that's actually useful in the real world. But we start simple, and we build. Okay, something I want to point out to you all is that remember the equation. So this is for a loop of wire. A loop of wire is B equals mu naught I over 2R. A very, very, very common mistake. If you remember the magnetic field due to a straight wire, it is the exact same equation, but with a pi on the bottom. That is the only difference between a straight wire and a loop of wire. And if you ever have two equations that look really similar, people will mix them up. So I am pointing this out to you all to just say be careful. When you're finding the magnetic field due to a loop of wire, do not use the equation for a loop of or straight wire. Use the right equation. Sounds obvious, but I can guarantee you that on the test, people will forget to put the pi for a straight wire, and people will put the pi for a loop of wire. Because if we go to our formula sheet, so in the formula sheet, I give you both of these equations. But I don't label which one's which. So if you all look down here, and we zoom in because it's really small. Okay, here's the one for an arc of wire. So this is an arc. This is a straight wire. And this is a circle of wire. Every single one just says B equals. This is kind of like before when I taught you the electric fields due to a point charge, a plane of charge, a line of charge, and a sphere of charge. Up here, there's 1, 2, 3, should be a fourth one maybe somewhere. Yeah, 4 equations for electric field. Doesn't say which one's which. Why do I do this? Because I believe if you all do the MCAT, they're not going to tell you which is which either. They will give you the equations, I think they do. They'll just say, here's a bunch of magnetic fields. So, anyway. Either write it on your note card or remember which one's which. Now, there is a little bit of a trick. Honestly, how do I remember this without using a note card or something like that? The magnetic field due to a loop of wire is stronger than due to a straight wire. Because if we look at a loop of wire, all the wire is really close to the spot. As close as it kind of can be. Well, uniformly. Whereas a straight wire, the ends of the wire get really far away from that point. So to that end, a loop of wire makes a stronger magnetic field than a straight wire. A loop of wire makes a stronger magnetic field than a straight wire. And the equations reflect that. The straight wire is divided by pi. The other one isn't divided by pi. If you divide by a number that's bigger than 1, you get a smaller number. So that's kind of the way I remember it. They're the same equation, but a straight wire is weaker, so I just picked the one that's weaker. The arc of wire has a theta in it, which indicates that, oh, I should have some angle. So there's little tricks to help you remember these things, to logic through it without having to memorize them. If you can think through, oh, that makes sense. A loop of wire is stronger than a straight wire, then the math matches that. The math should always match the logic. And depending on your brain is, pick whatever's best for you. Okay. The next slide, I am going to show you that you can find it at different spots, and then I'm going to tell you don't worry about it. Okay? So at the dead center of the wire, this is what you all need. It turns out you can find it along, say I take that center of the wire and I make a straight line through it. This is the equation for that. Look how awful it is. And that's still kind of nicer than literally anywhere else. And look at that, I even put a star. You don't need to know this. You do not need to know this equation, but just for funsies, if you get farther away from this loop, you can find it, and it's that equation down there. Woo. Moving on. Okay, main points. Feel free to look through the straight wire. This is kind of everything we've talked about so far. It's a nice little summary. Current carrying wires make magnetic fields. Awesome. Use right-hand rule for that. Wires going in opposite directions repel. We did the problem on that. Wires going in the same direction attract, meaning the current. If current in the wires is going opposite directions. Wires, looking at it, you can't tell which way they're going. Current carrying wires. We'll be a bit more fancy with our wording. Current carrying wires. If it's just a wire, who cares? It needs to carry current. And then there's all the equations, nice and summarized. Look at, you can see them all together. So this is just a nice summary on it. Okay. So now we're just going to do some practice. We're going to talk about, hey, if we have a couple wires, how do we find the magnetic field due to more than one wire? And then we'll get to the final geometry, which is, I told you all the whole having one loop. Why did I teach you one loop? Well, take the next step of that. What if I had lots of loops? And that's kind of going to be the next thing. So, anyway. Okay, so this is practice problem. It's from the discussion. And normally I don't pull stuff from the discussion, but it's a good problem. This is a good problem to kind of remember. A current carrying wire is kind of like analogous to a single point charge. If you wanted to find the electric field due to a bunch of point charges, you found it for each one, and you add them all together. If you want to find the magnetic field due to a bunch of wires, find the magnetic field due to each wire, and add them all up. It's the same logic. You start with something simple, and you just add up all the pieces. So I'm not going to do all three spots here. I'll do like a couple of them, set it up. So the question is, what is the magnetic strength and direction at points 1, 2, and 3? Let's start with point 1. Because it's point 1. All right, so let's label these wires. It's always good to label which one's which. That's 1, that's 2. Good job, us. Just makes our notation much easier. Call it A, call it B, call it whatever you want. What's given? So we're just going to look at the givens for point 1, because the givens are going to change as we do each problem. So we have the current in wire 1, that's 10 amps. We have the current in 2. That's also 10 amps. Oh, look at that. That's even nice. At this point, I'm not going to write any other givens. Let's actually discover what givens we even need, because that's going to be more aligned with what you will probably do when solving this. So, great, for now, that's my givens. You're like, but there's all these distances. What do I use? Let's find out together what we're going to use. All right, we are solving for the magnetic field at point 1. How do we do that? And let's reword this. The net magnetic field at spot 1. Oh, now that's going to get messy because I got wire 1 and wire 2. All right, let's call, I'm going to change things. Wire A, wire B, just to not confuse things. Okay, so we're trying to find the magnetic field at point 1. The key to this, each wire makes a magnetic field at that spot. Each wire makes a magnetic field. So if I want to find the magnetic field at point 1, I'm going to do BA plus BB equals B1. The magnetic field due to wire A plus the magnetic field due to wire B is going to equal that. Now, I actually have to check something. I just told you it was addition. We don't know that for sure. These are vectors. Vectors have direction. In fact, let's put little vector signs over these to remind ourselves of that. Vectors have direction. Remember, y'all, when you did electric fields and you were adding up vectors, direction mattered. To the right is positive. To the left is negative. Up is positive. Down is negative. So to that end, before I even proceed, we need to find the direction of the magnetic field at point 1 due to wire 1. Wire A, what direction? So pretend like wire B doesn't exist. Pretend like it doesn't exist. And I want you all to find the direction of the magnetic field at point 1. What's the direction of it due to a wire? So I have a wire carrying current to the right. What is the direction of the magnetic field above that wire? Is it up, down, into the page, out of the page? So we point our fingers in the direction, or thumb in the direction of the current. My finger's at the spot. It points out of the page. So wire A makes a magnetic field out of the page. And let's just color code these. We'll change A to being blue. So that is out of the page. That is a magnetic field due to A. Okay. Now we cover up the other one. What is the direction of the magnetic field due to a current carrying wire? The current is going to the left. My point is above it. What's the direction of the magnetic field above a wire that carries current to the left? Your thumb points to the left. My point is above it. Into the page. Yeah.
How can we ignore A if it's in between A and B?
So it's let me give you the analogy that you've done before. If I had two, so this problem is kind of like this one. I have a positive and a negative charge. What's the direction of the electric field at this spot? So we'd find the electric field due to the positive charge, that'd be away. We'd find the direction of the electric field due to the negative charge, and we'd add them together. It's the exact same logic as that. Yeah, it's a good question. Wire 2 doesn't care that wire 1's in between it. When, at least as far as point 1, we treat each thing separately, and the rule says we can just add up each contribution. Each one that contributes. They do not actually interfere with, okay, technically these wires would repel each other. We don't care about that. We're assuming that these wires are locked in place. Because technically they would actually repel each other, and we're going to assume these are rigid wires.
So we could use either A or B for 2, or we're adding them together?
We're going to add them together. Yep. It is literally, so this problem, what I want you all to connect is that at point 1, it's like what I drew in fact, let me even draw it. I say it's like this. It's a little different. I have a positive charge down here. I have a negative charge above it. What's the direction of the electric field at some point above it? What's the electric field at some point between them? What's the electric field at some point below it? It's the same mindset you all used for that, but the directions of these arrows is different. They follow different rules as far as which way they point. So, all right. So, wire B makes a magnetic field that is out of the page. Fingers to the right, or thumb to the right, fingers up. Sorry, into the page. So, to that end, I told you I added them, but the reality is, what is this actually going to turn into? First, you will have to define what's positive and negative. It doesn't matter what you pick. I'm going to say out of the page is positive. I'm going to say into the page is negative. Pick what you want. Just know what you define. So we're going to say out of page is positive. I think that's just kind of intuitively kind of nice. Into page is negative. And, I used the wrong colors for it. Whatever, it doesn't matter. Let's just do it in black ink so that we're not even confused. Out of page is positive. Into page is negative. So if we follow that rule, according to the picture I just drew, BA is out of the page, so that's positive. So I have BA, that's positive, plus negative BB, and that's going to give me my total field at point 1. That's going to give me the total field. That's the goal of this. This seems funky, like this may seem weird, y'all, but it's the same exact ideas that you've been using for adding electric fields. Find the two vectors, add them together. The only thing that's made this really weird is that we now have into the page and out of the page. But if I kind of just represent that to you all in class, so into the page, one of my vectors is like my arrow going in, another one's out of it, I'm adding those two arrows. They're opposite directions. So they're not getting stronger, they're canceling each other out. Okay? So, what's the equation for the magnetic field due to a current carrying wire? Due to a straight wire, it is going to be mu naught I, and then I think, is it the 2 pi r1 or the 2 r1? It's the weaker one, because straight wires are weaker than circular wires. So we put a pi on the bottom to make it weaker. It's just kind of my thought process for how I remember it. Okay. Let's go ahead and then build. So B1 is going to be mu naught I. So let's just rewrite what I had over here. In fact, I'm going to put it So BA plus negative BB equals B net. The next logical question, let's go ahead and get BA. So BA is going to be mu naught IA over 2 pi RA plus negative mu naught IB over 2 pi RB. And that's all I got to do is I just got to plug in those numbers. We have mu naught. We can add that to our givens. In fact, let's go ahead and take this whole thing and give myself some more room. So this is where I told you all we're going to go back and add some more givens, because as it stands, it's kind of tricky to see what the givens are or what givens we need. So we said at point, this is wire A, that made a magnetic field out of it. This is wire B, made a magnetic field out of it. Okay, mu naught, we know mu naught. Just throw that here. It goes 4 pi e to the minus 7. Give myself a little bit more room through the power of moving things around. I want you all, so we know IA, we wrote that down. We know IB, we wrote that down. We know pi, it's a button on our calculator. We know 2. I want you all to see if you can figure out what RA and RB are. It's from the picture. What is the value of RA? What is the value of RB? Spend like 30 seconds and see if you all can figure out what those are before I tell you. What is the value of RA? What is the value of RB? RA equals RB equals. So a reminder to you all, R is the distance from the wire to that spot. So RA is the distance from wire A to that spot. RB is the distance from that wire to that spot. So if we look at our picture, RA is this distance, which is 2 centimeters. Which is going to be I'll write 2 centimeters, so for those looking at this later, 2 centimeters equals 0.02 meters. RB is the distance from the wire B to that spot, which is 6 centimeters, 2 plus 4. Bam. And at this point, y'all, just plug and chug. So what was tricky about this problem? What was the new things I'm teaching you? 1, if you have more than one wire, find the magnetic field of each one and add them together. If they're in opposite directions, one direction is positive, one direction is negative. Left is positive, or left is negative, right is positive. Up is positive, down is negative. Out of the page is positive, into the page is negative. If you wanted to find out of the page is negative, that's fine. Just make sure you define into the page is positive. Like, you can define up as negative as long as you define down as positive. As long as you know they're opposites. If things are going in different directions, they don't help each other. They should cancel out in some way. The other thing I wanted you all to take away from this is how to find distances. So in the equation it said R. What is R? How far away you are from the wire. So, just putting it all together. Again, the last step is the least interesting. 4 pi e to the minus 7 times 10 over 2 pi times 0.02 plus negative 4 pi e to the minus 7 times 10 divided by 2 pi times 0.06. You plug that whole big thing in your calculator. It is good to practice the whole 4 pi e to the minus 7 times 10 to the minus 7. Again, the good news is you plug it in the calculator the exact way it's written. 4 pi e minus 7. Your calculator should have a pi button. If you use 3, just type the number 3.14. That's fine. Remember, as long as your answer is within like 1 to 2%, you're good. And something I will point out, you don't need to know this, but this may make your calculator calculating easier. If you pull out if you notice, y'all, both of these have the same, this is just a little math trick. Pull out your constants. You don't have to do this, but I'll be honest, this is what I am plugging into the calculator because it saves me time. They both had 4 pi times 10 to the minus 7. They both had 10. They both had 2 pi in the bottom. So instead of me typing them twice, I can pull them out and type it in once. Do whatever is best for you. But I'll tell you, this is what I am typing in the calculator because it's just quicker. And then I look at my calculator, and I look at what I wrote, and I check that they match, and I get a magnetic field that is 0.000067 Tesla. That can be rewritten as 6.7 times 10 to the minus 5 Tesla. That is a positive number, so it is out of the page. The direction matters. The end result, if you get a negative answer, that would mean it's into the page, based on our definitions. The final answer does tell you what direction the net force is, or the net field is. Whenever you're adding vectors, if it turns out positive, that means something. If it turns out negative, that means something. Direction matters when it comes to vectors. Positive, positive, out of the page. The good news for you all is I will not give you a problem where the magnetic fields are at angles with each other and you have to break into X and Y components. So when you all did electric field, remember I could give you a problem like, here's a charge here. Here's a charge here. Find the electric field here. And you had to break things into X and Y components, and it was so much fun. Magnetic fields, those problems are too difficult for me to make and explain well. So long story short, you're spared having to break things into X and Y components. You just need to make certain positive, if it's out of the page positive, into the page negative. Okay. Let's see. I am not going to solve the other two ones because that takes way too long. But what I will do for you all is, because I think this is the trickiest step, we'll just spend a few more moments finding the directions of the magnetic fields at the other two spots. That's not what I wanted. So here's my picture. Let's make it way bigger. I want you all to find, if we, again, same thing, call the top wire A, call the bottom wire B. I want you all to find the directions of both of those fields. Each of those wires makes a magnetic field. Find the field at point 2 due to each wire. Find the field at point 3 due to each wire. So, at point 2, does the magnetic field due to A point into the page or out of the page? At point 2, does the magnetic field due to wire B point into the page or out of the page? At point 3, same thing. Because that's the hard part. Do I add my vectors or does one of them become negative? That's the tricky part to this problem. So wire A, current is to the right, point is below it. Current is to the right, point is below it, so it points into the page. So wire A at point 2 points into the page. And there, swing 90. Wire B, current points to the right or to the left, points above it, it also points into the page. So what does that mean? It means both of the vectors will be negative. So when you are getting the net field here, so b at 2 equals negative b of a plus negative b of b. Because we just said into the page was negative. When you do point 3, same thing. Current carrying wire points to the left. We kind of already done this. The magnetic field due to A, you're still below the wire, so it is still into the page. If you're below the wire, it's going to still be into the page. And this one will flip because we're flipping to the other side. B, A, B, A, B, 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 B. So the magnetic field at point 3 equals negative BA plus positive BB. Okay. This is a great problem, y'all, for practicing this stuff. That's why, even though it's from the discussions, which normally I don't mention, this is a great problem for practicing this. Highly recommend it. All right. So I'll leave that for a couple more moments. At this point, yeah. That kind of covers half of what I wanted to get through today. If you have multiple wires, what do? This is what you do. The next question, this is the first thing we're talking about today if you have multiple wires. The next thing, the next half of the class is, remember, if we had a loop of wire, I said that's important. Why is it going to be important? What if we have a bunch of loops of wires? So that's what we're going to be building towards now. And remember, there's two components to that. What's going to be the strength of the field due to multiple loops of wire? What's going to be the direction of the field due to multiple loops of wire? So, what does the magnetic field look like around a loop of wire? Just a single loop. Let's see, where do I have this spot? At point P. Is this problem meaningful? Is this problem worth spending the time on? Yeah. Sure. That's fine. All right. Not super, okay, I told you all you're not going to do the math for this, but let's still kind of look at this. We talked about what the direction of the magnetic field was dead center. Take a guess, if I get farther away from that thing, what's the direction of the magnetic field at this spot P? It's farther away from it. It still lines up with it. Do I like this problem? Yeah, I'm just going to open this. I'll let you all think about it, and then I'll kind of give you the answer. I think this is not quite clear. But I think it's doable. What's the direction of the magnetic field at this point P? It's some distance far away from the center. So you can kind of see this. So I'm going to kind of talk through the answer as you're thinking through this as well. If we look, so it says clockwise instead. So the current is going clockwise up here. The current is going, it's going clockwise the whole time. So it's going to the right at the top. It's going to the left at the bottom. So we're going to use right-hand rule. We point our thumb in the direction of the current. So the current's kind of going this way. My point P is down at an angle. I swing my fingers 90 degrees. And I get a magnetic field that points this way at first. This is not the final answer. This is the magnetic field due to the top of the loop. If we do the same thing for the bottom of the loop, we point our thumb in the direction of the current. We point our fingers at direction P. We swing them 90 degrees. We get an angle. We get one that's pointed up to the left. Why does that matter? If you have something up to the left and something down to the left, the ups and downs cancel out. And so the answer to this problem, it's kind of hard to see here. This is the negative y direction. That's just the answer. Go ahead and select that. The net magnetic field is in that direction, inside it. There is a reason I'm bringing up this question, but We'll get to it once everyone's kind of put the right answer. So why did I give this really weird worded question? So inside the loop, it's also going this way. On the other side of the loop, it's also going this way. But what I want to point out to you, and you can kind of think through this as well. In fact, let's look at a permanent magnet, north and south. Magnetic field lines point away from the north, and they point towards the south. And if you've ever played with like magnetic filings, something that you're going to find is that magnetic field lines make these loops. They make these loops that go from one end to the other. Just like if we had a single wire, the magnetic field was a loop around it. These magnetic fields always make these closed loops. So if they're pointed some direction, and at the other point they point another direction, at some point they loop around. So the magnetic field, like the entire magnetic field around a single loop of wire, this is what it looks like. It makes these loops. It makes these loops. And why is this meaningful? If you just compare the two pictures I drew, you'll notice that a loop of wire looks a lot like a permanent magnet. And if something looks like something, that means we can make it act, we can use it like one of those. This is the beginning of making an electromagnet. This is the beginning of making an electromagnet. Is a single loop of wire basically is just like a permanent magnet. Meaning every application that a permanent magnet would be useful for, a loop of wire can do the same application. And that's going to have some useful applications for us as we get through this. But there you go. So that's kind of conceptually what I want to talk about. Let's see. Do I want to solve this problem? We'll get to this one if we have the time. I'm not worried about that right now. Great news. Notice how these slides are hidden? It's because there's an integral. So normally, if this is a calculus-based course, I would derive, again, I'd mention this, I'd say, Ampere's law, what a cool thing. We can use it to find stuff, woohoo. All right, for you all, I can't do that, so we're just going to kind of jump to the punchline. We're going to jump to this part and build it from here. So, I have a wire that is going out of the page. And now the wire is going into the page. What is the direction of the magnetic field at some spot in between them? I have a wire going out of the page. I have a wire going into the page. Oh my gosh. This question I never closed. All right, well, hopefully you all got the right question on the last one. Hopefully you didn't just change your answer. My apologies if you did. Life goes on. All right. Here's the new question. I have a wire going out of the page, a wire going into the page. What is the direction of the magnetic field dead center of them? And then I'm going to do my and then we'll build on that, and then I'll do my darndest to make a 3D. One of the biggest challenges with teaching this is representing three-dimensional things on a two-dimensional projector. If holograms ever exist, my life would be so much easier. But that's so far ahead. Well, my laptop charger is going to come in handy. So remember, y'all, do one wire at a time. Do one wire at a time. Find the magnetic field due to the top wire at that spot. Find the magnetic field due to the bottom wire at that spot. Do they add together or do they cancel each other out? That's basically so what direction do they point? And do they either add together or cancel each other out? Will kind of be the next question. Okay, look, they can't cancel out. None of my answers are 0. So, what a blessing to you all. All right, so we'll go to 140. In 5, 4, 3, 2, 1. Okay, so current carrying wire, I point my thumb out of the page, I point my fingers towards point P, I swing them 90, it's to the right. I look at the bottom one, my thumb points into my fingers point towards the point, I swing them, also points right. So, thumb points out, fingers down, swing right. Thumb points in, fingers point up, swing right. So, the top one we'll call wire 1, we'll call the bottom one wire 2. Wire 1 makes a field to the right, wire 2 makes a field to the right. They're exactly equal in magnitude, which at the end of the day doesn't really matter anyway. What matters is the net field is to the right. Okay. This is where I have to attempt to then connect this. Why did I ask this question? We've been talking about circles. Why am I talking about straight wires again? Well, if I take a circle and I put it here, this is a cross-sectional view of a circle from the side. The current goes out of the wire at the top and goes into the wire at the bottom. And your question is, what about all the other sides? Well, I just rotated the wire and it looks exactly the same. Doesn't matter, but the other ones also do the same thing. We've already talked about this. A loop of wire, they all add up together in the middle. So this is what a loop of wire looks like from the side. A cross-sectional slice. This is what a cross-sectional slice is. So now, what if I had a bunch of loops of wire from the side? What is the direction of the magnetic field at point P? I've got a ton of wires now. And notice I moved my point P a little bit up. Is it left, right, up, out of the page? Notice that none of the answers are like up to the right, down to the left. If I have a heck of a ton of loops of wire, just stack them. What is the direction of the magnetic field inside them? So yeah, this one's a loop of wire, this one's a loop of wire, loop of wire, loop of wire, loop of wire, and we're inside the wire. It's like a slice of it. What is the direction of the magnetic field here? The only thing that changed between this problem and the last one is we put a heck of a lot more of them, and we moved point P a little bit up. All right, we'll go to a minute 05. Close it out in 5, 4, 3, 2, 1. All right, so the good news is we've already done the wire above it and the wire below it. The wire above it pointed to the right, the wire below it pointed to the right. Now, the wire below it is a little bit further away, so it's a little bit weaker. If we now look at this wire, let's make that one green. Call this wire 3. This one points into it. We put a point P. That one makes one up to the right. You're like, that's kind of weird. Up to the right, but how's that going to work out? Let's look at wire number 4. That one is out through this point. Oh, that one's down to the right. If you have something that's up and you have something that's down, they'll end up canceling. And if you kind of repeat this for every single spot, you get this symmetry. For every wire that's up, every magnetic field that's up, there's one that's down. And long story short, I get a magnetic field that's to the right. Just like the last one. And let's see. Unfortunately, I don't have the math to prove this to you. But when this thing is infinitely long, so say I have an infinite number of these loops of wires, the magnetic field inside this thing, no matter where I am inside of this thing, the magnetic field points to the right and has the same value. This is, if you all remember the capacitor, the electric field was the same everywhere inside it and pointed in the same direction. In a capacitor, so one side was positive, one side was negative, positive, negative. The electric field was the same everywhere. Here, there, it was that way. Nope, that's the wrong direction. That way, doesn't matter where we are. This is our capacitor for magnetic fields. The magnetic field inside a coil of wire is the same value everywhere, and it points in the same direction everywhere. This is called a solenoid. You may or may not have heard that term before. A solenoid is what we have just invented. It is literally like a slinky. It's a coil of wire. A coil of wire. Now, it is very important that these coils either do not touch or are made of an insulating material. Why is it important that they're made of an insulating material? I need it to go in a circle. If they're not insulated and they're all touching, why would it go in a circle? It will just go from the top to the bottom in a straight line, and I've just made a tube. It's not very interesting. It'll just, a tube that current goes. So, this has to be an insulated wire. And you coil this thing. We define how many coils there are by N. Capital N is the number of turns. Capital N is the number of turns. Number of turns. So if I coil this thing 50 times, that's capital N. L is the length. If I divide the number of turns by how big the thing is, I get the number of turns per meter. Turns per length. Kind of like how tightly coiled is it. These are two ways that you'll see this. You'll either say, hey, here's how many coils it has, here's how long it is, or here's the number of turns per length. Literally, just think of what that word means. How many turns per length? The more turns per length, the more coils I fit in a spot. And we're going to find that that makes a stronger field. So the closer you can get these wires together, the better. All right. Solenoids are extreme. This is an electromagnet. This is basically every single electromagnet you've ever seen is this. It's a coil of wire. This is how you make strong magnetic fields. An MRI, how does it make strong magnetic fields? It's got big old solenoids in it that are made of superconductors that can let you run a ton of current. Your headphones have a solenoid in them. How do they make music? You have a solenoid and you have a permanent magnet. When I make that electromagnet make a field one way, it pushes the magnet one way. When I make the current go the other way, it makes the magnet go the other way. You can make that magnet vibrate at a very specific frequency. Ta-da, you made music. Music is just very specific frequencies of vibrations. If you can make every single instrument that ever exists, all it's doing is making air vibrate. Your headphone is literally just something inside it vibrating at a very specific frequency. It's controlled by the current. So when the current goes one way, it pushes the magnet one way. When the current goes the other way, it pushes the magnet the other way. And it does that super quick in a very precise way. So these are all over the place. Electronic locks, this is how, well, say electronic locks. This is how, like, one way to lock a door, that's another way. These are in all sorts of circuits, and they literally look like this. They look like a cylinder. They kind of look like, they look like a coil of wire. These are the biggest things in a circuit. They're in all sorts of circuits. All right, so here's the equation for it. Very simple equation. Mu naught, capital N, number of turns, I, current, L is length. If I divide N by L, so remember y'all, lowercase n is just N divided by L. Mu naught, lowercase n times the current. The more current, the stronger the field. The more turns per length, the stronger the field. That's the only variables that matter. Distance, where you are in this coil, does not matter. Dead center, same field as if you're right up inside, like right up near the edge of it. Inside the coil. And they all point in one direction. The magnetic field all points in one direction. How do we find the direction? Right-hand rule 2.5 is our nice little shortcut. So, for example here, just coil your fingers in the direction of current, boom, magnetic field to the left. Right hand rule 2.5, just curl your fingers in the direction of current. The magnetic field will point in this specific scenario to the left. So that's where right hand rule 2.5 is really useful for solenoids. So this is kind of what everything was building to. No one is building electromagnets out of straight wires. No one's building electromagnets out of arcs of wire. This is the practical app. How do you make a strong magnetic field? This. Any magnetic field that is strong is not coming from permanent magnets. Electromagnets are how we make those 1 Tesla fields. For an MRI, those 10 Tesla fields. And you can turn these on and off. That's the other power to this. You can't turn a permanent magnet on and off. It just is. Now, you can break a permanent magnet, and I don't mean literally hit it with a hammer. I mean, you can demagnetize it. Fun fact, how do you demagnetize it? You heat it up. You can demagnetize a magnet by heating it up. It makes all the different, remember everything lined up. If you heat it up, now it's all random again. It's no longer a permanent magnet. I suppose, well, I won't get into that. They demagnetize things in Stranger Things. It's hand wavy at best. Technically, if you put an opposite magnetic field, you can demagnetize something. But to do that at long distances would be like so wildly strong that you'd have bigger problems than magnets falling off fridges. But whatever. That's just classic TV. Who cares? Okay. Let's see. Great. Let's do a practice one. So we saw the equation. In fact, here it is. B equals mu naught capital N over L times I. And then I reminded you all that, I will remind you that lowercase n, there you go. So just practicing using these equations because the units are a little funky. Like this whole turns per length, what is that? Once you see enough times, it'll make sense. But yeah, solenoids are all over the place. They're in your phones in some capacity. You will eventually learn this is how wireless charging works. That'll be next week. Wireless charging relies on solenoids to make an alternating magnetic field. We'll learn why alternating magnetic fields are important. But again, everything builds. Everything we talk about builds on each other. This week we started with a single straight piece of wire makes a magnetic field, and this is kind of the major punchline. You coil that thing up, you can make a really strong field that's consistent. And there's tons of applications for strong magnetic fields. Next week we're going to get into, we'll talk about a little bit of them today, and next week we'll talk about another whole category of usefulness to these things. It's one of the reasons I love Physics 2 a bit more than Physics 1. Physics 1 application is kind of like, I toss a ball and I can predict where it's going to go. It's not nearly as interesting as like learning how electric motors work and circuits, and in my opinion, teach their own. All right, we'll close this out at 2:20. Give it a few more moments. I think everyone's already done it anyway. All right, so we'll close this out in 5, 4, 3, 2, 1. All right, so putting all this, so lowercase n is 200 turns per meter. That was really the only challenge here, is recognizing that is lowercase n, not capital N. Capital N is how many turns. L is how long my solenoid is. Lowercase n is turns per length, which is just those two things divided by each other. Bam, comes out to 7.54 e minus 4 Tesla. Remember, Gauss is technically a unit per magnetic field, but not the unit that gets spit out when we use these equations. Okay, so connecting this. So last week I told you all about, hey, electric motors. If you have a magnetic field and you have a current carrying wire, we can make it rotate. And that makes a motor. And I mentioned that there's like these brushed motors. And I mentioned the phrase brushless motors, meaning they don't have brush in them. This is what it looks like. And this looks crazy. But we'll just kind of unpack this, like, again, we're going to watch a video in a video. Well, for those online, you're going to watch a video in a video, and it's going to be very weird. I'm not going to play this too much, but seeing it in motion is going to explain all that chaos that it just looked like. Don't worry about all the graphs on the side. Who cares? Let's see. But what we're going to point out here is how this thing is functioning. All right. Again, it's having a very hard time streaming a stream. Okay, whatever. This is good enough as long as I can rewind it. Okay. So, here's what's going on here. You don't need to know any of this, but it's cool. These are permanent magnets on the inside. So these are permanent magnets. Not electromagnets, permanent. They literally, neodymium, whatever. Strong magnets. These are the electromagnets. These are the solenoids. Notice how there's those loops of wire. So what's going on here is I have multiple electromagnets arrayed around this thing. Why? Inside of it, I have magnets. The red is, let's say, north. The blue is, let's say, south. If you've ever played with magnets, the north and the south end attract each other. You ever play magnets north and south? Opposites attract. So, looking at what's going on here, at the top, when I make the current go a specific direction, I turn this electromagnet basically into a south pole magnet. Remember, in a solenoid, depending on the direction of current, if the current's going one way, the magnetic field is one way. If the current's going the other way, the magnetic field is the other way. So I can flip-flop the direction of the magnetic field. So here, they make the magnetic field like a south pole, north and south. It attracts this red magnet here. On the other side, I make a north pole. I make the current go the other way. It repels this. So this part here in this circle is getting attracted to the right, repelled to the right. Now, at some point, if I leave this as is, it's just going to stay there. So, look what happens though as time goes on. So as time goes on, it's getting attracted right here. It gets turned off. So it's no longer attracting this spot. But this red one is still pushing it to the right. Oh, look, we turned this one on to that south pole. So it's going to attract this. It's attracting it. This one just flipped to red. So now it's pushing this in. So it's just this cycle of push-pull, push-pull, pushing and pulling at the right times so that this thing keeps spinning. Notice here, again, attracting, turns off. Now this one's attracting it. When this one gets closer, this will turn off. And the next one will start attracting it. So it's just constantly pulling it along, This is an electric motor. It just keeps pulling it along in a circle. And the stronger this is, as time goes on, it gets faster and faster and faster and faster and faster. And these things cycle quicker and quicker and quicker. Nothing is touching. This is why it's called a brushless motor. Nothing is physically touching. The fields are doing this. And so what this means, brushless electric motors don't wear out, really. The only things that contact is in the middle here. There is a bearing. Skateboards have bearings. It's spinning, so something's got to spin. But this outside and this inside aren't touching at all, which is kind of cool. Anyway, this is how every single electric motor is actually designed. More complicated than the one before, but way longer lifetime to it. And it's all based on magnets that we can turn on and off and change the direction. What do we call a magnet that we can turn on and off and change the direction? A solenoid. So, it's cool stuff. Feel free to kind of watch through this if you want. These graphs, don't worry about them. They will just confuse you more than they're worth if you want to look into them. But if you're interested, this video is on here. Super cool. It'll teach you how electric motors work. 90%, that's being generous. 97% of people don't know how electric motors work. And yet they use them almost every single day. Your spark plug is also a solenoid. That's a whole nother thing. All right. This one. This is fine. This is a good problem because it takes two ideas and puts them together. It looks worse than it is. A solenoid with 250 turns per meter carries a current I. An electron moves within the solenoid in a circle. That should be a trigger for you. Charge moving in a circle. In a circle that has a radius of 2 centimeters and is perpendicular to the axis of the solenoid at the speed of the electron is 2 times 10 to the 5 meters per second. What is I? Seems complex. Let's draw a picture. Pictures always make things easier. So, I'm going to draw a cross-sectional view of a solenoid because otherwise I can't draw here's a solenoid. It's going to be a little tricky to draw an electron inside that and not be very confused at what's going on. So sure, I'll draw this, but the reality is, so I've got some current going out of the page. I've got some current going into the page. This is my cross-sectional. We're looking inside the solenoid. I've got an electron making a circle. There's my electron, and it's, making a circle. And I'm struggling to make that, there it is. Doesn't matter which way the circle's going for this problem. Circle's got a radius of 2 meters. So R equals, not 2 meters, 2 centimeters. I'll put the 2 cm. The velocity, it's kind of, I'll just start writing my givens because it's kind of tricky to draw the velocity on here. So velocity is 2e to the 5 meters per second. The radius is 0.02. Just went ahead and converted that centimeters. Lowercase n is 250 turns per length. So turns per meter. Okay. And that's all we have givens-wise. We technically have mu naught. We always have mu naught, but I want you all to spend a few moments. Think about what equations might we use here. What concepts might we use here? Pause and think about it. Give you a hint. There's a solenoid, and I'm going in a circle. Those are two kind of triggers for what equations are going to come into play. If you ever see a solenoid, there's literally only one equation that has to do with solenoids. If you ever see something going in a circle, there's something that immediately should come, that you're always going to use if something's going in a circle. What are those two things? Oh, we're solving for I. We'll go ahead and... Not that it really even matters. What we're even solving for, the things I just told you, doesn't even matter what we're solving for. Your mind should immediately say, solenoid, there's an equation. Circle, there's an equation. So we'll start with the one that's the most fresh. The magnetic field due to a solenoid is mu naught lowercase n times I. Just gave that to you once, so hopefully fresh. Okay, that's solenoid, great. And then last week, I gave you the equation that if something is going in a circle, QVB equals mv squared over r. mv squared over r is the centripetal force. QVB is the force that a moving charge experiences. So this equation kind of combines both of those. It says the force that a moving charge experiences causes it to go in a circle. That is a very important concept for you all to remember. If a charge enters a magnetic field, it will go in a circle. If a charge enters a magnetic field. And actually my picture here isn't the best, because this circle is not the path that I showed you here. This circular path would actually be, so if this is my solenoid, the circle is actually going to be going like this, inside the solenoid in this path. Now, how do I draw that well? It's not an easy way for me to draw that. I guess we could view it from the other side. So in fact, sure, let me draw it a bit more accurately. So really, what's going on here, this is kind of my solenoid, and my charge is doing that thing. whatever. Doesn't really change much. But I do need you to know that charges in a magnetic field go in circles. Charges in magnetic fields go in circular paths. And there's why. We talked about that last time. It's a great thing for you to look over and remind yourself of. At this point, y'all, it's just math. We've kind of, again, once you identify the equations that you're going to use, you're kind of good to go. As far as how to choose the equations, if you see a solenoid, use the solenoid equation. If you see it going in a circle, you're going to use that. That's just guaranteed. Now, there's a couple more givens we need to write down. Remember, if you don't always have, like, if you ever get the equation like, oh, okay, so B, I don't know B, but I know mu naught, I know N, we're solving for I, which means I'm probably going to have to find B. How can I find B? Oh, look, there's B. Q, what's the charge of an electron? 1.6 times 10 to the minus 19. Cool, got that, got velocity. Mass, oh, what's the mass of an electron? Let me make sure this is an electron. Yep, 9.11 times 10 to the minus 31 kilograms. Cool, got that, still have velocity, I've got the radius. I've got so I can solve for B. Then I can plug that into the other equation, and I can solve for I. So, that's what we'll finish with. So QVB equals MV squared over R, so 1.6. I'm going to go ahead and cancel out this V with this squared. Save myself a little bit of writing. Times B equals 9.11 e to the minus 31. Times 2e5 over 0.02. You do some algebra and you get the following answer. So we'll divide that 1.6 times 10 to the minus 19 to the other side. We get a magnetic field that equals 5.7 times 10 to the minus 5 Tesla. Cool. Now we take our other equation. So 5.7 e to the minus 5 equals 4 pi e to the minus 7 times 250 times I. Just divide the things to the other side and you get an answer. So this is kind of like what I ended last class with, in that it takes two concepts, one from this week, one from last week, and puts it together. Really good practice. If you can do a problem with one of these concepts by itself, awesome. If you can do a problem with another one of these concepts by itself, awesome. If you can do a problem with both the concepts together, that means you really understand it. That means you understand how to, two-step problems are kind of like as hard as it gets here. 0.18 amps. And there you go, y'all. I don't know why I had 2 slides after this, but that's it, y'all. So, what did we learn today? If you have more than one wire, find the magnetic field of each wire, combine them, being careful of directions, and solenoids. It's a bunch of loops where the magnetic field inside it is constant and the same direction. And they're super, super useful. Good luck, y'all, with this. We got one more week of magnetism, and then spring break. And then we'll have our test after spring break, the Thursday following spring break. So don't forget about that, y'all. Shoot me emails if you got questions. I may or may not check my email during spring break. Probably not that much. Keyword there is break.